Well, our next lesson, unfortunately, is more computational methods for solving differential equations. Well, I'm sorry, but sometimes you have to do that. But if we're lucky, we maybe can find either some software or some built-in functions to do this automatically. Worst comes to worst, if you look on this website, poke around down below, you can find, not only can you find a program that runs on a TI 85 or 86, it can be adapted to whatever your calculator is, or written in Fortran, or written in, what are the modern programming languages? Let's say written in Java, written in C++, anything that handles the scientific. You could probably do this yourself, and if you are interested, you can even use a spreadsheet and set up a spreadsheet to do this. Okay, one of the more accurate numerical methods, more accurate than Euler's method or improved Euler's, for solving this numerically, that means we're producing a table of values, is called fourth order Runge-Kutta. The idea comes from the Taylor series with the remainder discussed in the last section. See, this is the Taylor remainder. Recall that a function can be expressed as a Taylor polynomial of degree n with remainder as follows. Here's the remainder. Here's the function y of a, y prime of a times x minus a, y 2 primes of a over 2 factorial times x minus a squared. And the reason why it can be expressed like this is because the function and all its derivatives up to order n agree, and this is the remainder for what doesn't agree. And c is some number between a and x, and c is picked as part of this Taylor. Remember how to find that, a number between a and x, and that's it. So the remainder part is the error in representing the function with its nth degree Taylor polynomial. The Euler method in the last section let n be 1. So if you recall, we were approximating the function with its tangent line. So we stopped here. But with Runge-Kutta, we can do better than that. By the way, the error was on the order of h squared, and that's actually the local truncation error. The error on the global was order of h. And so that is, in fact, a first order Runge-Kutta method. Second order Runge-Kutta methods go like this. Consists of finding constants a, b, c, and d so that the formula is y sub n plus 1. In other words, our next guess is the last guess plus some number a times k1 plus some number b times k2, where k1 is h times f of x and yn. In other words, the function evaluated at the old guess, and k2 is the function evaluated at the old guess plus that number c times h plus some number d times h. And so if you can find the a, b, c, and d to do that in such a way that agrees with the Taylor polynomial of degree 2, and if the constants a, b, and c are satisfy a plus b equals 1 and b times c equals b times d equals 1/2, if we were to choose a times a equals b equals 1/2 and c equals d equals 1, we have in fact the improved Euler, or the Human's formula from the last section. Remember the y1 star, yn star, etc. And so that is something we've already done. The improved Euler, though, is just one of an infinite number of second order Runge-Kutta. Pick different values for a, b, c, and d, and we get another one. And what that is doing is finding a weighted average of, we just found the weight with equal weights, but weighted average of the slopes of the tangent lines to get our next guess. And the local truncation error, if you recall, on the order of h cubed, and the global on the order of h squared. Which, you know, if we had a h equal 0.01 or 0.001 and we're using a computer, good gracious, the global would be on the order of 1/1,000,000th for the error. You know, but no one could do that by hand, but a computer can do it just fine, or a spreadsheet could do that just fine. So think about that. Third order Runge-Kutta methods, and there aren't any assigned problems where you do a second or a third. Well, the second you do in the last section, but but this is a third order, and the constants used now when to predict our next y, we use the old y plus 1/6, and that's going to be a weighted average of all these tangent values. If you could follow that, you're a better man than I. But really, that's That's a weighted value of all those tangent values. Oh, sorry, I guess that was a bit rough. But if you're using a computer algebra system, fourth order Runge-Kutta is likely to be a built-in program, as it is with my MathCAD software. And look on the website, there's a program for fourth order Runge-Kutta. You can set up a spreadsheet to do this, not very hard. And an alternate approach, right, do that. And an internet search should return a couple sites with spreadsheets as well as instructions on use. So when I make an assignment, if you want to do it with a spreadsheet and turn that in, that's perfectly all right. So fourth order Runge-Kutta, which is the one we're going to use, uses this same kind of average. And it actually uses a Taylor polynomial of degree 4 to approximate the function. And therefore the local truncation error is on the order of h to the fifth, the global on the order of h to the fourth. So if a small h is chosen, you can see the resulting accuracy. So MathCAD has a built-in function. I'm going to use it, since that's what I'm using. You can use your calculator, you can use built-in stuff, you can probably download a Runge-Kutta somewhere off the internet to do it. The arithmetic is tedious. I'll use it once to solve our problem from the last section. Y prime is y minus k, y0 is 2, and y of 1 is what we're trying to find with a step size of 0.1. So here's how MathCAD does it. I define my function y minus x, that's the derivative, right? And that's how you define the differential equation you're going to be working on. Make it y squared minus xy plus blah 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 blah, something we couldn't normally solve, and we'd still have a way to solve it. So S is our Runge-Kutta fixed. The 2 means our initial y. The 0 is our initial x. The 1 is where we're going to stop. This is the interval 0 to 1 for x. We're trying to find y of 1. And the 10 is what describes, we're going to take the interval from 0 to 1 and divide it up into 10 pieces. So that's how we get our h equal 0.1. And the d is this d right here that we've already described. So this makes a table of values, and from x0 equals 0, and every time it adds 1/10 for n equals 0 to 10, and the column at the bottom right side can be compared to the solution that we already know. It should be 2 plus e, and 4.718. That's pretty good. By the way, I tried to make it more accurate than that, and I can't see a way to do that. But this agrees quite handily to 10 to the negative 3. And of course, if you go back, it's probably even more accurate than that. So remember, this is error on the order of h to the fourth. So 0.1 to the fourth power is 0001. And so you can see that we're accurate at least that far. Actually, that we only have 3 digits accuracy in our table here, so that turned out to be quite good. Doing one by hand is not an option. Okay, so here's another option you could do, is use the web asset called Wolfram Alpha. I think that's it. And that has a built-in RAK4 to solve our equation dy dx equals y minus x using step size 0.1 and initial conditions y0 equals 2 to estimate y1. And I'll try to match the browser window with mine, and you'll be able to see that in the next video.